Lesson Markov Decision Processes. Markov decision processes are a foundational concept in decision-making theories and have been integral in the development of artificial intelligence, particularly in areas like reinforcement learning. An MDP provides a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision-maker. Professionals in the AI field can leverage MDPs to optimize decision-making processes in a variety of real-world applications, from robotics to finance and healthcare. At the core of an MDP are the elements of states, actions, transition probabilities, and rewards. A state represents the current situation or status of the system. The set of all possible states is known as the state space. Actions are the choices available to the decision-maker at each state. Transition probabilities determine the likelihood of moving from one state to another after an action is taken. Rewards are the immediate gains or costs associated with state transitions, guiding the decision-maker towards desirable outcomes. To apply MDPs effectively, practitioners must construct a model that accurately represents the problem at hand. This involves defining the state space, identifying possible actions, quantifying transition probabilities, and determining reward structures. For example, in a robotic navigation task, states could represent the robot's location, actions could be movements in different directions, transition probabilities might account for movement uncertainty, and rewards would be assigned based on proximity to a target location. One of the most practical tools for solving MDPs is dynamic programming, specifically algorithms like value iteration and policy iteration. Value iteration involves iteratively updating the value of each state based on expected rewards until convergence, providing an optimal value function. Policy iteration, on the other hand, alternates between policy evaluation and policy improvement steps to find an optimal policy. These methods, though computationally intensive, are powerful in deriving optimal strategies in environments where the model parameters are known. In practice, applying MDPs requires addressing challenges such as state space explosion, where the number of states becomes too large to manage effectively. Techniques like state aggregation and function approximation can mitigate these issues by reducing the complexity of the state space or approximating the value function. For instance, in online advertising, where the state space may include millions of potential user profiles, function approximation techniques using neural networks have proven effective. MDPs are also key to understanding and implementing reinforcement learning, a subfield of machine learning where agents learn to make decisions through trial and error. In RL, the agent interacts with the environment, receives feedback in the form of rewards, and uses this feedback to learn an optimal policy. Techniques such as Q-learning and deep Q networks are based on the principles of MDPs. Q-learning, for instance, is an off-policy algorithm that learns the value of an action in a given state without requiring a model of the environment, making it suitable for many real-world applications. An illustrative case of MDPs in action is Google's use of reinforcement learning to optimize the energy efficiency of its data centers. By modeling the cooling system as an MDP, Google developed an RL agent that could predict and adjust power usage, resulting in a 15% reduction in energy consumption. This case highlights the potential of MDPs in RL to drive significant efficiency gains in industrial settings. Another practical application is in autonomous vehicles, where MDPs are used to model decision-making processes for navigation and obstacle avoidance. The state space includes the vehicle's position and velocity, while actions involve acceleration, braking, and steering. Transition probabilities account for uncertainties such as road conditions and other vehicles' behaviors. By optimizing the reward structure to prioritize safety and efficiency, autonomous systems can make real-time decisions that balance various factors. In healthcare, MDPs are employed to optimize treatment strategies, particularly in chronic disease management. For instance, in managing diabetes, states can represent a patient's health status, actions include different treatment options, and rewards are based on health outcomes and costs. By employing MDPs, healthcare providers can personalize treatment plans to improve patient outcomes and reduce costs. Implementing MDPs requires proficiency in both theoretical understanding and practical application. Practitioners should be adept at using software tools such as MATLAB, Python, and R, which offer libraries and frameworks for modeling and solving MDPs. For example, Python's MDP toolbox provides a suite of functions for policy iteration, value iteration, and Q-learning, facilitating the application of MDPs to complex problems. Moreover, understanding the limitations and assumptions of MDPs is crucial. MDPs assume full observability of the environment, meaning the decision-maker has complete knowledge of the current state. In many real-world scenarios, this assumption does not hold, leading to the need for partially observable Markov decision processes. PMDPs extend the MDP framework to handle situations where the state is not fully observable, adding complexity but also increasing applicability. To effectively implement MDPs in professional settings, it is essential to follow a structured approach. Begin by clearly defining the problem and objectives. Construct a detailed model of the environment, specifying states, actions, transition probabilities, and rewards. Choose an appropriate solution technique, considering factors such as computational resources and the complexity of the problem. Validate the model by testing it with real-world data, iteratively refining it to improve accuracy and performance. In conclusion, Markov decision processes offer a robust framework for decision-making in uncertain environments, with wide-ranging applications in AI and beyond. By mastering the principles and tools associated with MDPs, professionals can enhance their ability to develop solutions that optimize decision-making processes, drive efficiency, and improve outcomes across various domains. The integration of MDPs with modern machine learning techniques continues to expand their potential, making them an indispensable part of the AI implementation toolkit.